So I want to begin this by introducing to you guys something we call series circuits. All right, so R represents resistor. R represents a resistor or resistance. So if you see R1 over here, that means the first resistor. Now a resistor is anything that electricity can flow through. So it can be a light bulb, right? If you take a look here, these light bulbs, now you can't quite clearly see what it is, but there is a light bulb over here. So these light bulbs, you can say, are resistors. Anything that uses electricity can be called a resistor. Your phone is a resistor. Your computer is a resistor. Your microwave, your refrigerator, your air conditioner, your printer, anything that uses electricity is a resistor. And we represent that with a zigzag line on a diagram, right? So we represent that with a zigzag line. Any questions so far? Any questions so far? Okay. All right, all right, all right. Let's take a look at this now. So U, now explained in the slide, U represents potential energy. This G right here means gravity. So this as a whole, U sub G represents gravitational potential energy. And as you recall, gravitational potential energy is mg delta H. Now, why is it U? That's because it's a symbol used in college. All right. Now, but we use P, right? We use P. So the gravitational potential energy, if you recall, increases as you go up, right? As this person lifts this object, he increases the gravitational potential energy. As you as you and as it falls, right? As it falls, you lose gravitational potential energy. As you can see by it filling up, right? Okay. And so I want to make that same analogy here. Well, U sub E represents electric potential energy. UE represents electric potential energy, all right? So as you run, so before that, now remember, due to the terminology we still use based on Benjamin Franklin's work, sometimes people still draw it as protons moving. But I've continually said in class that, right, protons do not move. It's actually the flow of electrons from the negative side to the positive side. All right, just keep this in mind when you're looking at these gifts. It is not the protons that are moving in reality, but it is the electrons. All right. So what happens when you move? What happens to electric potential as a electron goes through a resistor? Resist is not a battery. The epsilon represents battery. Think of a resistor as, like, again, it's resisting the flow of electrons. And you need energy to push these electrons through the resistor. So your electric potential energy here, right? Your electric potential energy here decreases as you run through a resistor. Does everyone see this? Is everyone okay with this? As an electron goes through a resistor, your electric potential decreases. But what provides the potential difference in the first place? What provides this potential energy? It's not a question related. It's not in the question, right? Yeah, the battery. The battery is the one that's providing a potential difference. Again, to move electrons, you need a potential difference, a source of potential difference. Which brings me, and is everyone okay with number one? Did everyone finish writing down the answer to number one before I move on? Please raise your hand.
I didn't get the answer, sorry.
So the answer is, again, your electric potential decreases, okay?
Okay, thank you.
Hold on, someone is spam calling me. Answer number two. Okay. Let's see what you guys put down for number two. Number two.
Wait. For one, right? I'm looking at it again. For the resistance, does the lines on the resistance, does it represent the electron? Or like when the electron drops completely?
No, the
Is that the
resistor
representation?
represents. Wait, what?
For the number one, when I'm looking at it again, for the resistance, right? It's the lines is going to like a zigzag formation. Does it represent the electron, or does it just or does the electron just drops when it goes to it?
It represents the zigzag lines represent the appliance or whatever object you're running electrons through. The zigzag line is meant to represent the fact that as the electron goes through an object, it hits things, which lowers the current and lowers the potential. That's what the zigzag line is supposed to represent.
Oh, okay.
Okay, all right. Let's see what your answers are. Right? Let's see what your answers are. So you're all on point. Yeah, you're all on point. Right? The electric current decreases as you add more resistors. Right? Because your resistance, as you add more resistors in a circuit, your resistance goes up and your current goes down. Good. Now do number 3, guys. You haven't been introduced to parallel circuits yet, but I want you to see like if you can come up with a difference between series and parallel circuits. I just want to see. I just want to see if you can do that. You thought everyone learned this in middle school? You can learn circuits in middle school. It really depends on what middle school you went to, though. So what over number 2? Where were you this entire time? I think you can answer yourself. I'll be honest with you. You don't really need me to answer number 2. You can answer number 2 yourself. Just by looking at the gifts, you can answer it. I'll tell you if you're right or not. It's gonna mute her. I think she. All right, let's see what your answers to 3 are. See what your answers to 3 are. Cool. All right, fine. So, fine. Some of your answers are fine. So the main thing here, the main difference, right? The main difference with which I wanted you guys to realize that if you have circuits connected in series, there's really only one path for electrons to flow through. In parallel circuits, on the other hand, there are 2 pathways, right? In one circuit, there's only one pathway. In series circuits, there's only one pathway. And in parallel circuits, there are multiple pathways in which electrons can flow, right? So that's really the main difference here. In series circuits, there's only one pathway in which electrons can flow. And in parallel circuits, there are multiple pathways in which electrons can flow. Please don't move on to 4 before I tell you to. All right, please don't move on to 4. Now, you can pretty much tell that I'm basically speed running this because I'm skipping a lot. So now we get to number 4. What do you think is one advantage? What do you think is one advantage in having circuits connected in series over circuits connected in parallel? It's not an aesthetic reason, it's a practical reason. It's not for aesthetics, right? It's not whether or not something else looks better or not. It's actually a practical reason.
A series circuit is actually much easier to make than a parallel one
Okay.
because you just have to put them all together. It's just one wire.
Okay, not wrong. Let's see what your answers are. Yes, fine. Okay. Again, it's not an aesthetic reason, guys. It's not aesthetic. So here's the thing, right? Let me just posit a scenario, right? Current in a series circuits run through these wires, right? So go all the way there, go for each light bulb, and then go back to the plug. In parallel circuits, on the other hand, right? In parallel circuits, on the other hand, the current runs through each light bulb and pass through one another. Well, they don't really connect to each other light bulb. They run through the light bulb and go back to the plug. Right? The electric current doesn't run through each of these other light bulbs. The current just goes through the light bulb and then out. Now, the advantage here is that, well, if one of these light bulb breaks in a parallel circuit, for example, if this light bulb stopped working, then the rest of this would still work. electric current would still flow through the rest of the circuit. Whereas in a series circuit, if one of these light bulbs stopped working, right? If, for example, if this light bulb stopped working, the rest of this circuit would not have an electric current anymore. No more electric current would run through the rest of this circuit. And so the circuit would stop working. For example, right? Behind every wall is a switch. I mean, right now, behind every wall is a circuit. Right? Behind every wall is a circuit. I'm sure in your home you've had switches before. Right? You've had a switch. How do I draw a switch? I think this is how I draw a switch. You know what? Fine, whatever. Anyway, and maybe you've had switches like this. Maybe they look like this. Right? Maybe it looks like that. Where you just basically flip it back and forth. What this switch actually does. What this switch actually does is that it lets electrons flow through the circuit, right? Right, this switch over here, you're basically opening and closing a circuit, which allows electrons to flow through. A parallel circuit, on the other hand, right? If you look at this, a parallel circuit, on the other hand, even if you close off one switch, right? Even if you were to stop electricity running through one wire, the other one would still work. It doesn't matter if I open or close the switch right here, the other one still works. So having multiple pathways is much better than having one pathway. Modern light bulbs actually have something that modern light bulbs have, even if in the event that the bulb breaks, right? In the event that the bulb breaks and this thing like suddenly breaks, there's actually some other metal connection, another path in which electricity can go through. So if this light bulb blows out, right? If this light bulb blows out over here, and it can't go here anymore, there's another path for electrons to go through, and it's through another path. So that's a modern light bulb. That would be like that would be a modern light bulb. So the disadvantages of series circuits are then gone. Now, I'm going to tell you guys right now. If we were to learn the math, we would spend basically 3 to 4 days on this each. We would spend 3 to 4 days on series circuits, and we would spend 3 to 4 days on parallel circuits. And we would spend a really long time going over these two things. Because there's a lot of math involved in circuits. The concepts are okay. If you think the concepts are bad, then you would have hated the math. I'm letting you guys know right now. And this formula would come into play. So there are also, and let me just give you an example of something else. In series parallel circuits, it's like a combination of these two. Like there's like 1 pathway, 2 pathway, 3 pathway, 4 pathways. But then in each of these pathways, you have like a light bulbs connected in series. I think an example of this, I'm not too sure, but I'm pretty sure. Not too sure, but I'm pretty sure. Is those lights, right, in a classroom. You know those lights at the top, and you would like they're like three panels. And then each of these light panels at the top are separated into like 3 more. And then there are light tubes over here, right? In each of them. This is an example of a parallel circuit. Because think about it. How many times throughout your time in NYC DOE schools have you never seen a light bulb or light panel go out? Like you turn on the lights and instantly this stops working. One light panel stops working. Even though one light panel stops working, the other panels still work, right? The other panels are working, but for some reason, one light panel just doesn't work. So you can think of it like that, right? You can think of parallel circuits like that, right? They're not connected by any means. I mean, they are connected in parallel, but they're not connected in series. Man. Any questions, guys? We're gonna end this off with a video and no more questions. There are 2 videos here, but actually, let's just watch this. Actually, no, the 6-minute one. I'd rather watch the 6-minute one. First off, there's no audio.
When a pilot lands at night, runway lights guide him in safely and reliably. Airport designers choose a particular kind of circuit for these lights, called a series circuit. That's what we'll be looking at in this segment of Physics in Motion. A circuit, as we've learned, is simply an electrical pathway that makes a loop. A series circuit is a closed loop in which the current follows one single path. The components are connected along the path, kind of like in this string of lights, and the same current flows through all of them. The wire from the plug joins one bulb to the next bulb, to the next bulb, to the next bulb, then back down the wire in one continuous loop. So the bulbs are in the same series. You know how when one goes out, all the rest of them do too? That's because if you interrupt a series circuit, it's toast. The path is broken and the current can't flow. Let's make our own series circuit using this battery type, some miniature bulbs, and some wire. I'll explain more about series circuits, which are the simplest of circuits, as we go. First, let's run a wire from this power supply, which is our voltage source. When the battery provides energy to make the current flow in the wire, we measure the current in units called amps, named after a famous physicist, Andre Marie Ampere. Now the bulb. The bulb has a filament with high resistance, making it hard for the current to flow through. The unit of resistance is named after another famous scientist. You remember his name, George Ohm. The symbol for ohms is the Greek letter capital omega. You'll see this symbol whenever we draw a resistor on a circuit diagram. Resistance creates friction, which makes the filament heat up and glow. And voila, light. In our one power supply, one bulb setup, we can see that the current has only one path to follow. That's what makes it a series circuit. No matter how many components we add, the current only flows on one path. This is a diagram of a closed circuit, meaning there are no breaks or switches, so the charge flows in a continuous loop. One more thing, the voltage drops as it's used up by the bulb. The more voltage is lost, the brighter the bulb shines. Now let's add another bulb in series. What changed? The number of bulbs. What didn't change? The battery and the wire, the voltage, and the current's path. Voltage, current, resistance, the 3 interrelated properties of Ohm's law. We can use Ohm's law to show what happens mathematically.
Don't worry, guys. don't have to learn about the math, okay? No math is involved. Not learning about math.
when we add an identical bulb to our circuit. In this equation, the voltage across the single bulb circuit equals the voltage across the entire two bulb circuit, which equals the current through the two bulbs times the combined resistance of the two bulbs. We know that our overall circuit resistance doubled when we inserted a second bulb, shown in this equation. Resistance in the two bulb circuit equals 2 times the resistance of the single bulb circuit. This means the current in the circuit, which is constant throughout a series circuit, is half of what it used to be. As a formula, that is, the current in the two bulb circuit is
Yeah, is the rest of this video formulas? It is. Well, I mean, you know what? Let's go to let's see what the intro for the parallel one is.
It's hard to imagine what life would be like without our ability to harness electricity, to light our buildings and run our endless array of electrical powered devices. In another segment, we saw what a simple circuit called a series circuit looks like. We saw that the more bulbs you add, the dimmer the bulbs because the voltage is being shared across them. And if one went out, they all did. So how did we get to this? So many lights, all delivering equal amounts of voltage. And when one goes out, we simply replace it, while the others continue to shine. The answer is an ingenious kind of circuit called a parallel circuit. It's a simple, logical solution to provide the basic wiring we need to supply electricity to our communities. A parallel circuit is a closed circuit in which the current divides into 2 or more paths.
Am I pronouncing it wrong? She says it parallel. I say it parallel. She says it parallel.
Before recombining to complete the circuit. Each resistor connected in a separate path receives the full circuit voltage. The total circuit current is equal to the sum of the individual branch currents. Let's build a parallel circuit.
I think this is just going through more math. This is going through more math. Okay, guys, make sure you finish all 4 questions on the go formative. All right. I wish you guys a very, very, very good weekend. All right. I wish you guys a very good weekend. Have a great weekend. Bye-bye.
Bye. Have a good week.